All right. So the focus now is the second lab, which is on expressions. And let's go take a look at that. I think we started talking about this last time, some of these ideas. Idea of a data type. You know, when you declare a variable, you declare it an int or a double, so on. The difference between a primitive and a complex data type. Let me bring up our work from last time. It was on, I'm using this Cloud9 system, which I recommend to everybody at this point. It's working, seems to be working fairly nicely. So we were looking at some work here. We didn't save much, did we? Yeah, we made a copy into lab 2. So we started on lab 2 here. What is this? Oh yeah, here's code that that shows how to prompt the user for something, for information, and the user enters it in. And then we use that information. So we ask, you know, we print out what is your name, and we declare a variable called name. It's of type string. String is a complex data type. And then we declare another variable, int x. Int is a primitive data type. Double y, that's a double precision floating point value. So we have a decimal. We have a fractional component to the number, right? X has no fractional component. It's just an integer. So double is also a primitive data type. Now I'm going to comment these lines out. This is a single line comment. I could have used a multi-line comment as well. Let me show that to you. Slash star, that opens the comment, and star slash, that closes the comment. As you can see in this editor, it displays that text in green, so indicating that that is a block of text that's a comment. And name is a complex data type, which means that it has operations on it that you can access through this dot operator. So I can query the length or the size of the string. That gives the length of the string. That's an end line, so I'm going to print an end line character. I need to save that. So I can see that icon up there shows me I need to save. I think I'm in lab 2, so I CD into lab 2. And there's the code. So let's build that. C++, what is it? ex1.cpp. That generates a dot out. Let's run that. This is what is your name? That's the prompt up here. Then it prints number 0. That's because name has size 0. So that's, with a complex data type like a string, you can interact with the data using this dot operator. So it has, these complex data types have specific data type specific operations. Well, all data types have data type specific operations. But this has operations that are accessed, also called functions. They're also called functions. Operations and functions are the same thing in this language. And but you cannot do that with x. You can't say x dot size, because x is a primitive data type. We don't have access to a dot operator with X. Let's prove that by trying to compile, and it fails. Request for member size in X, which is of non-class types. A non-class type means it's not a complex data type. But there's X, nevertheless, X does have, it has a value in it. We could do this. It has 0 in it. But it doesn't always have 0 unless we initialize it to 0. So to play it safe, we do this. In C++, you need to initialize variables. Otherwise, their state is unknown. We're just lucky to get a 0. Most languages will 0 the X. If we declare X as an int, most languages will initialize it to 0 automatically, but not in this language. There's another sense of size of X as well, and you can use this size of operator. I can do size of X. I think that its syntax is valid. Let's check it. See, it actually comes in gray. I don't know if you can see that. What's this going to print? Anybody know? Any guesses? I did give the information last time. Yeah. 1? No. 4. 4 bytes. And int is 4 bytes. What happens if we did size of y? 8, good. 8 bytes. So the size of operator tells us the number of bytes that are allocated to store an instance of that data type. Can I do size of string, size of name? I don't think so. I don't think this is defined. I don't think size, it might be. It is, wait a minute, I think this is defined. Now I'm getting off into some advanced topic here. So this is going to be, whoops, oh my gosh, it closes so easily. I don't know what I did. Alt-Q, I think. I think I hit Alt something. I hit Alt something or Command something. Size of name. I have to guess at this. It's going to be something like maybe 8. I'm taking a wild guess there. Not too wild. It's 4 or 8, something like that. 8. I got it. Look at that. Because it's storing a pointer to an allocation in the heap. This is what I thought. I think it stores a pointer to an allocation in this heap. And it also stores a pointer to a list of functions. Something like that. Something that has to do with inheritance. And I don't remember all the details or the terminology for it. So that's why I guessed an 8. Because I looked at, some years ago, I looked at what the compiler generates when you create an instance of a complex data type. But if name were set to something big, there's a lot of bytes there, right? Each character, if these are single byte characters, which they are, there's more than 8. There's more than 8 characters there. But we're going to get the same size. It's not going to show some number. It's still going to show 8. Because it's showing us the size of the memory allocation on what's called the stack. And this, four of the bytes in this allocation of 8 bytes is pointing into an area of memory called the free store or the heap, where memory is used flexibly to represent these strings. So there's some memory in this off of what's called the stack inside the heap, and it's expandable. It can contract and expand to store, different size strings. But that's not reflected in the size of operator. Now, this topic I mentioned as I started, I bookmarked there. This is an advanced topic. You don't need to know this. Later, some of you will need to know this, but not for this class. I just thought I'd fill in some details there of an advanced nature. Okay. Let's go back to here. So we talk about primitive data type, complex data types, the string data type. You need to do a little research on that. There's other parts of string data type that you should know about, like substring. I'm not sure what this. Let's get the word big here. How do we get the word big? Well, this I is position 0. Oh, by the way, counting in computers generally start counting from 0. So if a computer wanted to count everybody in this class, it would start 0, 1, 2. If it stops at 2, it says, oh, there's 3 people here. That's how a computer counts. 0, 1, 2. Oh, that's 3 people. And that's how we'll be counting in this class. We'll be creating these loops that start with this index value set at 0. You'll just have to get used to that. Most languages follow that idiom. Because at the hardware level, that's how computers work. Counting starts at 0. It's a product of the way the hardware has to work. Or not has to work, but logically should work efficiently, the way it would work efficiently. So this is position 0. This is position 1, position 2, 3. That's position 4. So the B is in position 4. It's the 5th spot, but because the first spot is labeled with a 0, the 5th spot is labeled with a 4. So we say it's position 4. And I don't always remember what the format of substring is. What comes next is either the number of bytes or the last position or the end position. Does anybody know what it is?
Yeah, the starting one, whatever you're starting from, is the first one, the second one, where you're ending.
Say it again?
So 4, you're starting at 4, and that will just whatever you're ending to. So I think you had it right where end position.
End position? You don't think it's number of bytes? You think it's end position? Because different languages do it differently. I know that JavaScript and C++, I think they do it differently. So one language, they give the number of bytes in the second position, in the second argument. In other languages, they give an end position. So you're saying it's an end position.
Well, it's whatever you're starting from, and then counting how many positions
Oh, counting. So would it be 3? But is it going to be 3, or is it going to be, let me see, 4, 5, 6, or is it going to be 6, or possibly it's 1 past the position we're interested in, which would be a 7. Which one of these statements generate the word big? I'm pretty sure that the first argument, these, by the way, this is a function or an operation on the string data type. I want to extract a substring from a larger string. That's what this is used for. And I am pretty sure that the first argument to that operation, or that function, is the starting position in the string where you want to take the substring out of. But the second argument, I can never remember because it's different across different languages. That's why I get confused. So in the first example, we want to extract 3 characters starting at position 4. In the second example, we want to extract the characters at positions 4, 5, and 6. In the third example, we want to extract the characters at 4, 5, and 6. I'll put a 7 there because the command is expecting a position that's 1 past the end of the substring we want. And sometimes in these APIs, that's what you need to do. So which one is it? 1, 2, or 3? Does anybody know? Well, you got to take a guess. I'm going to guess. I don't know. I can't make a guess. I don't know which one it is. I guess we don't have to take a guess, right? Let's see which one it is. The second one. Oh, no. Oh, I'm sorry. It's the first one. It's the first one, right? Like we have 2 spaces here. That's why here we printed 2 spaces. And the last one, we printed the 2 spaces and the R. But in the first one, we just print big without the period. So it must be this one. This must print big. And it's a little confusing to see this because we didn't print a new line there. Oops. Big, big, big R. All right, so it's the first one. It's this one. So the second argument must be the number of characters. There it is. All right. How to change the state of a variable using the assignment operator. Well, that's pretty straightforward. Oops. I almost hit that key again. That closed my window. Here we assign 0 to x, but we could reassign it the value 3. So that equal sign is the assignment operator. We're assigning the value 3 to the variable x. When I say variable x, I mean x is a label for a storage location in RAM. Not in this disk drive, in RAM. It's a location in RAM memory. That's what x represents. Although one could say sometimes x is being manipulated in a register and then copied back out to RAM again. So temporarily it could be in a different spot. So this is an example of the assignment operator. All right, what about other stuff? Understanding mathematical operations. The C++ operator precedence. So this chart here shows the relationship between operators in terms of their precedence. So this is this is a double equal sign. We'll be using that a lot in this class. This means compare 2 things. Compare 2 expressions. If they're equal, then evaluate the true. If they're different, then evaluate the false. This is called a logical operator. And that has, what do we call it? Higher precedence? It has lower precedence than plus. Let me show you what I mean by that. I'll leave that in there like that. So I'm going to do, x equals 0. You see that? This is an expression. Actually, this will evaluate to, let's do it like this. I'm going to do it like this. True and false. If x equals 0, then print true. Else print false. So this is called a conditional. This is a conditional expression. It's like you have a branch in your logic. We're either going to print true or false. We're not going to print both. So as you look at the program here, look, these statements, these are like activities that you're asking the computer to do. We're asking the computer, print out what is your name. And then what do? We just go to the next line. Now we say, create a variable called name, initialize it to, I'm big, really big. And then we go to the next, you see, we do it sequentially. So these statements are executed sequentially. And that's how the computer goes about doing things. It goes to do things sequentially. Except when it hits something like a conditional, where here there's a branch. It's going to, it has a condition. The condition is that x equals 0. If the condition is true, it's going to execute this statement. Otherwise, it's going to be false. Otherwise, it'll execute this statement. So it's a little break from the normal sequential processing. Yeah.
You can use else if.
You can also use else if, yeah. Of course, that wouldn't make, yeah, we could do it like that. Let's do that. I'm going to show an else if. Else if x equals 1. Just to change the example. So if x is 0, we're going to print 0. Else, if x is 1, we'll print 1. Else, we'll print something else. And that's a variation. I was showing you the simple else if. This is the simple if else construct. This is a little bit more complicated. You have a question?
Yeah. Can you just keep adding else ifs in the middle?
Yeah, you can just stick them in there. Yeah, I'll do that. Oops, that's not what I wanted. There we go. You can just keep going. And there's an alternative to the syntax called the case statement. I'm not going to get into it. If you're a computer science major, you better read about it. You'll need to know what a case statement is, but I'm not going to get into it. You'll eventually, if you're going to get into programming, you'll get to a case statement. You'll have to understand that. I almost never use case statements. I don't like them, but some programmers love them. And you're never an island unto yourself. You're always working with someone else, or you're reading other people's code. So you got to know how to read all different kinds of styles. Yes. All right. Oh, let's test this, by the way. What is this? When I run the program, what does it print?
0.
Yeah, it prints 0. Good. it's also printing what is your name. Let's get rid of that. That's really irritating. What if we assigned 1 to x? That's an easy one, right? Now it'll print 1. And if we assigned something else, it'll say something else. Now, let me show you a common mistake here. What if we did this? Instead of doing comparison, we're doing assignment there. The compiler should complain about this, but it doesn't, okay? It does the assignment, and the expression evaluates to 0. Remember I told you about how when you look at statements, they evaluate to something. This expression evaluates to 0. It assigns 0 to x, but it also evaluates to 0. And 0 inside of a conditional is interpreted as false. So it will not print this. Let's explicitly make x 0. We make x 0, we have this conditional with assignment. So there's a bug here, like a logic error, but the compiler is okay with this. What is this going to print? This is kind of advanced. I wouldn't ask this on the exam, by the way, but you know, since we got here, let's finish the job. What's it going to print? Now, let me tell you that this is an old language. New languages don't do this. This is a mistake. We're doing assignment when we should have been doing comparison. Comparison is double equal sign. So this assignment assigns 0 to x and then evaluates to 0. But 0 is interpreted as false in the conditional. So it will not print this. Then it comes to here. Then it compares x to 1, but x is 0. So this is false. So then it goes into the else branch and it prints something else. That's my hypothesis. And I'll tell you, I'm confident about my hypothesis. Every quarter I'm confident about my hypotheses or hypothesi, whatever. But I'm always wrong at least once every quarter, so I'm always humbled, just to let you know. But I feel this is going to print something else. All right, works. All right, here's a test. What does this code print? Something else? Good. Well, good in the sense that I agree with you. Let's see if we're right or whether we're going to be humbled. Yeah. And why is that? Because here we assign 1 to x. But in this statement here, we're accidentally assigning 0 to x. So now x changes its state to 0. So when we get to the second condition, x is now 0, so this is false. All right, that was another thing I was going to try. What was that? I think that's it. Moral of the story, watch out for your double equal sign. When you want a comparison, this is called a comparison operator. Make sure it's a double equal sign. It's a common mistake. A newer language would warn you about that, or would fail to compile. Because in C++, this comparison, this expression, which is a comparison, actually computes to an integer. It's either 0 or non-zero. I think -1 usually, or always. I'm not sure. 0 and non-zero. So the conditional computes to an integer. It's stored and manipulated in memory as an integer. But in other languages, like Java, for instance, you know, there's no automatic conversion from Boolean values, which is the true-false value. It's called Boolean. There's no automatic conversion from true-false expressions to integers, although internally it's probably stored as an integer. But the compiler will refuse this. So in Java, for instance, in other languages, C# and many others, this will not compile because it's expecting a Boolean expression here, but you gave it an integer expression. They'll say, I can't do this. I can't compile that. But in our language that we're using here, C++, we don't get that. So it's a little hard. It's one reason it's a little harder. There's a lot of reasons this is harder. Now, why do we do this in C++? Why do they, you know, do better checking in Java, for instance? Anyone know why? Well, I know why. Let me tell you why. C++ is old. It's just an old language, and newer languages always fix problems from older languages. It's an old language. Why bother learning an old language? Well, there's a ton of code written in this old language. So and that code has got to be read, it's got to be maintained. And so there's just a need to know this language. All right. Now what are we going to do? Am I recording? Yeah, I think I am. So this is the chart of operator precedences, and I'll talk about it as we go along. The const keyword. Maybe we want to do something like, if we go const, that's short for constant. We can declare x as a constant variable. So this compiles, it's going to print 0. But if we do this, what's it going to do? Try to stay alert. I'll ask questions, I'll let you think. Huh? No, it never even gets there. It doesn't even get there. It won't compile. The compiler's going to say, hey, you told me x isn't going to change, and there you're trying to change it right here. I said, yeah, but you told me up here. So you're breaking the contract, programmer. So I'm not going to generate an executable here. There it is, compilation error. It's not a logic error. Like we were just looking at logic errors. We're doing assignment instead of comparison. That's called a logic error in this context. In Java, it's compilation error. Now we're getting a compilation error. Compiler won't even generate the executable. So that's const. We learned about string, how to call functions. We talked about that already. The Boolean data type. Let's talk about that. All right, there's another data type called bool, which is short for Boolean. Boolean means a true or false. You know, an int, you can have -30, you know, 0, a million. Those are integers. You can't have 1.2. You know, 1.2 is not an integer. It's not part of the integer data type. The bool data type has only 2 possible values, true and false. So we'll call z a Boolean. Set it to false. So we can do something like this. You know, we have z is declared. So we could say, you know, if we set z to true, we could set z to true here. And z is set, I say z is set to false, okay? And then we change it to true. So it'll print true. There it is. Or we could set it to, you know, seven, what's it, 22 over 7. That's, people used to use 22 over 7 to represent pi, right? Z 22 over 7 equals, or is less than pi. What's pi? Well, let's get a long one there.
3.141592653.
Holy cow, I'm going to just copy, okay? That's good, you got that all in your head. That's a great achievement. All right, so is 22 over 7 less than that number or bigger than that number? I mean, it could actually be equal to that number too. But I got to tell you right now, I have a bug in this code. Does anyone see the bug? Huh? No? Oh yeah, by the way, see how many operations are in this statement? Can you count them? Don't forget about the parentheses, that's not an operation. How many? Any other suggestions? 3, that's the one I like. And there's assignment, see, people forget about that, that's an operation. This is a computing language, it's not a math. We're not writing math here, in a sense. This is not a math equation. This is an operation. That's assignment, that's an operation. This is division, that's an operation. And that's less than, that is an operation. These are 3 different, very different operations. This is an arithmetic, division is an arithmetic operation. It results in a value, in a number value. This is not an arithmetic operation. This is a logical operation. Is that right? Maybe it is arithmetic. It's a comparison operator. Do they call that an arithmetic operator? I don't think that's an arithmetic operator. Anyway, this doesn't result in a numerical value. This results in a Boolean value, true or false. Either the left-hand side is less than the right-hand side, or it's not. So it's true or it's false. This is called a Boolean operation, or a comparison operator. This is a division operator. This is an assignment operator. Its purpose is to change the state of a variable. But these are 3 different types of operators, and they have precedence compared to each other. We have to understand what is the precedence here. 3 operators, the computer's not going to do all of them at once. It's going to do one, then the next one, and then the third one. Which one does it do first? It's going to do division first. And that next operation? Less than, yeah, or comparison, we could say comparison. Then it's going to do assignment. And, oh, by the way, this is not even needed. I could change it. I could do it like this. Once again, then that would force the less than operator to run first. Now, this would be a compilation error in other languages, smarter, more modern languages. In C++, although this should be, we think of this as a Boolean value. In C++ language, it really computes to a 0 or a non-zero. So this will be, you know, a 0 or a non-zero. If it's a 0, then we're going to divide by 0. We're going to get a fault there, a runtime fault. Actually, the compiler, these are constants, so the compiler might catch it for us. I'm not sure. Anyway, that's getting off on a tangent, which you want to do sometimes. So look, the result is this. What gets stored in Z? What are the, false or true? We don't know. False or true. The thing is, when you see that there, Z is not a number. You shouldn't think of it, I mean, it is a number in the sense that C++ is an old language and numbers are used for Boolean values. But you should think of this not as a number, you should think of Z as a Boolean value. It's a true or it's a false. So, let's make it false. Oh, but there's a bug in there, and someone hasn't noticed it yet. All right, is this going to be true or is it going to be false? It says true. Huh. It says true. And watch this. This is that number right there, isn't it? And, oops. It's 22/7. That's the number, that's 22/7, right? That's what we did here on this calculator. Looks like 7 is bigger than 3.14, isn't it? Look, 3.142. So 22/7 is a bigger number. But why is it coming up true when I say less than?
You got stuck in degrees?
Degrees? No, I didn't know degrees here.
It did the comparison of 7 to 3.14, and then
No,
it
It
did
did-
true instead of false.
it didn't. No, it didn't do this. Well, this would be false. Would be 0. This would be a runtime error probably. It would say, division by 0, or I don't know, whatever it's going to say here. Actually, warning. It's a warning. They still compiled it. The compiler, because these are constants, these 7, there's no variables there. It's a constant. The compiler went ahead, tried to generate. The compilers they perform optimizing operations. So, the 7, this operation's not even in the executable because the compiler said, oh, this is just 2 constants. I'm going to compare them now and decide whether it's true or false, and then use the result. And it said, hey, wait a minute, buddy, you're trying to go 22 divided by 0. Well, I'll generate your executable. That's why it says warning. But I'm going to tell you that it doesn't look right, because when you run it, you're going to get some kind of a floating point exception. Anyway, that's getting off on a tangent there. We got to get back to here. This should print false. All right, let me tell you what it is. What is this operation right there called? Wait a minute. In C++, there's, on all languages, there's 2 kinds of divisions. There's integer division and floating point division. And that's true for all languages. Unfortunately, we only have one symbol, slash. It'd be nice if we had 2 different symbols, one for each of those operations, but we only use one symbol. One of those mistakes that were made not a mistake, but something that was chosen or decided on in the past. You remember in the past when languages were first developed, the set of punctuation symbols and characters was very limited. They didn't want to use this. They didn't want, as another example, they didn't want to use equal sign as for assignment. But what you got a keyboard here, typewriter keyboard. There's no they liked the arrow. They used arrow a lot in the old days to show assignment, but there's no arrow on these old systems. Well, there's not any arrow on a new one either. So let's use the equal sign to represent the assignment operation. Just like that, there's 2 different operations here. This floating point division, integer division. Now, integer division means you throw away the fractional part. So this, how does the compiler sees that and says, oh, the numerator is an integer, the denominator is an integer. The two operands are integers. Therefore, this programmer must want integer division. But this programmer doesn't, but it thinks we do. So it's going to say, well, the result will be an integer. So what's 22 divided by 7? 3. Because you toss out the fractional part. This is a very common mistake. That's why I'm making a big deal about it here. This will happen to you many times. So you just make one of the constants there look like a floating point number. Now the compiler's going to go, oh, you're using a decimal point, even though it's .0 and simplifies to an integer. The compiler's going to consider that a floating point value. If at least one value in the expression is a floating point value, then the operation is considered floating point division. We could do that. We could do both. We could do the denominator. One of them is good enough. Okay, now we fix the logic error. And this is not just C++. All the languages are going to do this, except for scripting languages. All right. Now it should come up false, right? It should come up false. There we go. All right, we figured it out. So lots of lessons there. One lesson is the distinction between floating point and integer division. That's one lesson. Another lesson was the order of operations. That we could alter the order of operations with parentheses. See, we did that. And then we got, what do we get? We got a floating point division error. Right? Floating point exception. So divided by 0. And also the concept of Boolean data type. This assignment, Z is not a number. You shouldn't think of it as a number. I mean, it is in C++. In Java, it's not. But never, regardless of that fact, that you should think of Z as not a number. You should think of it as a Boolean value, true or false. When I say number, I mean integer. Sorry, it's not an integer or a floating point value. Because you can think of true and false as forming a number system and all that stuff. Anyway. So that's that. What about so that's an expression. We could also say Z equals Z equals false. We could just assign it false directly. We can do that as well, which we did in the initialization up here. Another thing we could do is, why bother with Z at all? Let's just go ahead and use that expression directly in the if statement. We don't need the Boolean variable declared. Let's see again, these conditional statements, these if statements, operate on expressions that evaluate to true or false. This evaluates to true or false. Oh, let's see that. All right, we're flying out of time here. All right, how to use conditional expressions, we did that. How to compare integers, floating point numbers. Learn how to write loops and use them to solve problems. Loops. A difference between floating point and integer division, got that. Learn how to round floating point values to the nearest integer by adding 0.5. And so I want to talk about this one and loops. Actually, what I want to do is talk about, yeah, let's do these exercises, 3 and 4. Generate a list of 100 random integers, okay? Let's print 100 random integers. So this is exercise 3. So I made a copy. This is nice, little interface here, it's good. And I'm going to show you how I think you should start your problems. Okay? I'm going to do cout OK. I'm just going to print, I'm going to run a hello program or an OK program. Just to see that everything's set up, that the compiler's running. Look, there, right off the bat, I got an error, right? What's that? Oh, yeah, thank you. Thank you very much. Good. My hearing is a little weak, but everybody said something at the same time. All right, there. See, that's step 1 right there. You see, I'm going to show you incremental development procedure here. Now, what we want to do is we want to print 100 random integers. That's what we need to do. Oh, what does it say here? 100 random integers. Oh, we're going to need this. Because we're going to use a rand function. It's going to give us a random integer. I'm sorry, a random integer. And let's take a look at that. So rand is a function. I'm going to call the function. Let me do it a little differently here, just to show that to you in 2 steps. Rand returns an integer. Maybe I like I for integer better than x. That sounds like a floating point value. All right, here we're calling the function rand. When you call a function, you use the function name, like sine or cosine or rand, and then you have arguments. Like if it was sine, it would be like sine of 90 degrees. Well, actually, it's not degrees, it's radians, 90 radians. Sine of 90 radians. All right, so sine takes 1 argument. If I did this, the compiler would say, hey, sorry, sine doesn't take 0 arguments. You're missing. It won't compile here because you're missing a required argument. Rand is a function that takes no arguments. See? Well, we need the parentheses to tell the compiler it's a function call. It's a function that you invoke without passing any information into it. That generates a random integer stored in I. Now let's print I here. There's a random integer right there. Oh, the same random integer. It's a pseudo-random number generator. What we got to do is we need to seed the random number generator with by calling srand. We seed it with a value, say 0. See, rand displays or produces a sequence of integers that are not truly random. So we call it a pseudo random number integer. So pseudo means you're pretending to be something. And but it'll generate the same string for a given seed. So you can set the seed here with srand. Let's try that. Let's see if we get a different random number. We get the same one. Let's change the seed to 1. We're getting the same value? What's going on? What is going on? See, I lost my confidence up here now. Things are not going right. It always happens. That one's different. 0 and 1 give the same value. And let's try a 3. Get my confidence back now. That one's different. Now look, if I don't recompile, I'm still using 3 as our seed. So it keeps producing the same number. So if you really want your program to look random, the normal process is to pass in the current time. And this time is a function. It takes arguments. When you pass in a 0, you're saying, I want the number of seconds that have elapsed since some epoch. Usually it's, the first second of 1970. That's the typical epoch. But it doesn't matter, just some random value. Now, I don't think I need to declare a header for time, but on some systems you might need that. Like, there it is, see? Watch this. That's a different one, right? See, I have to wait at least a second. If I do them really fast, let me see if I can do it really fast, all in 1 second. Yeah, there it is. I got 2 I ran the program within 1 second of the, the system clock. Get 2 numbers that look the same. But now it's a different second here. So that's one trick. So now the problem is we want 100 of these. We're only producing 1. Well, another thing is we don't need I here. I'm just going to put rand right there. Why have a variable when you can just use the result of the function and use that result directly in this output operation? There it is. It's looking good. Still works. All right. So we want 100 of them. And I mean, you could do this, right? You can do 100 of these. That's not too bad, right? There it is. Should be a different list every time. All right. Now we're not going to do it that way. So on the test, I might ask for 1,000. So you got to have a loop. So let's do the loop. The loop looks like this. While some condition is true, repeat a block of statements. And just to show you that it's a block and not a single statement, I'm going to do it like this. We're going to see out rand, and we're going to see out a new line. So here's a block of statements. As long as the condition is true, we're going to repeat the statements over and over again. As soon as the condition is false, we're going to stop doing it. However, a condition evaluates the true or false. If we put true in there, we got an infinite loop. This will run forever. Let's see that. And we might get into trouble here. Oh no, what do we do? Tell me, help. I think Control C. It might not work. See, I'm locked out. Control C. Uh-oh. I crashed it. See, it's a different environment. It's buffered a million of these things. Ay, ay, ay. I probably get an email from the company now. What did you do? You ran out of RAM? All right. Let's see if I can kill it. Are you sure you want to close this terminal? Yeah. I hope that's not still running in the background. All right. Yeah, but on my local machine, you know, I could kill that. And, apparently, the way their system works, they let the program run and run up some output buffer. So they had an extra buffer, which had a lot of capacity, and we just maxed out on it. All right, so what are we doing? Oh yeah, this condition. We want the condition. We want to do 100 of these. We want a condition that's true 100 times and then becomes false. So we need a counter, see? So as soon as we finish the statements, we're going to increment this counter. We're going to call it I. We need to declare that, by the way, integer I. I'm going to set it to 0. So I'm going to do it the human way. And then I'm going to show you the way you typically see it in code. The non-human way. We need to learn to think like robots in here. Not become a robot, just understand how a robot thinks. All right, so the condition is this: while I is less than or equal to 100. Do you see that? If we start I at 1, and then we do the statements, and then increment I, is that going to work? So we have 1 here. When I is 1, we do this. Then I becomes 2, and we do this. When I becomes 100, we still do that, and then we quit. Yeah, that's 100. But actually, just to make sure our reasoning is correct, let's just do 3. It gives us 4 or 2. We know we're off by 1. Right? There's a famous problem, a conceptual problem in computer science called the off by 1 problem. You're always faced with this problem. When you do these calculations, you don't know if it's like calculating your birthday. Like, how old am I this year? Well, is it after my birthday or before my birthday, right? And I got a different age based on that. So just knowing the year isn't good enough. I could be off by 1. So off by 1 situations happen all the time. So this is an example where I could have been off by 1. That's why I went through that thinking process. I wanted to make sure I got it right. And then I wasn't off by 1. Well, I'm going to do better than that. I'm not going to count 100 numbers to see if I was off by 1. I'm going to set this to 3 to see if I'm off by 1. Let me do this. I'm running out of time here. Looks good. We're not off by 1. But what if we did this? I mean, it's conceivable that you could have wrote your code like that, right? Well, it's the same thing, isn't it? This doesn't matter. This gives us the same result. So there's no off by 1 danger at all here. So I take that back. It always gives us 3. It doesn't matter where you increment the I. But normally we increment the I at the bottom of the loop. That's how we think about it. So that's how it's done in there's an equivalent form for this. It's called a for loop. For integer, I'm going to use k in this case. For integer k equals 1, k is less than or equal to 100, plus k. And we're going to do these 2 lines. This is an equivalent loop. This loop and this loop here, they give the same result. They both generate a list of 3 random numbers. The for loop is more compact. See up here, how many lines do we have? 1, 2, 3, 4, 5. We have 6 lines here. We have 4 lines. So the for loop is more compact. So in this particular case, the for loop is better because it's simpler to look at. But sometimes the for loop does not work well because you have a more complicated condition. the thing the condition depends on is simply incrementing a counter or something else. Yeah.
You use a for loop when you know your commit, the precise increments you're going to do, and you use a while loop when you don't know.
Yeah, that's one example. But I think for loops are good when, yes, something like that. There may be some variation to that rule there. That makes sense. See, the for loop, oh, this is 100. Okay, well, we got it going 100 now. Now the for loop, I'm running out of time here. I hear clicks and everything. What am I going to say here? I'm going to try to skip to the important stuff. Oh yeah, this is important. Normally the counting, I'll talk more about for loops next time, but what I want to talk about, what I want to finish with is the while loop up here. And explain that this isn't how we normally do it. Normally we start the counter at 0, not 1. And the condition is that we're less than the number of times we want the loop to run. So this loop here runs exactly 3 times. We start the counter at 0, and we exit the loop when it gets to be 3. Same thing for the for loop. You'll almost never see a for loop like this. You just won't see it. Sometimes you see it. But seasoned programmers sample code online. You know, most of the time you won't see it like this. You'll see it like this. And that's a reflection of how the computer itself is thinking internally. Now, originally programmers were writing in machine instructions, then assembly code, then they hopped up to Fortran and C, and they just kept that tradition. Let's make our expressions the same as what the hardware is doing. So this is how that looks, and I think we ran through everything here. Oh yeah, this last problem. I got to tell you, this is not an easy problem here. But we don't have time to look at it today. I'll look at this problem on Wednesday. And but in the meantime, you should still try this. And it's a good problem to think about. It's kind of got me in the past, but I got to figure it out now. Anyway, I don't want to run on. That's it for today.